Good morning, students. In the previous lecture, we came to know the concepts which are playing a crucial role in developing a Verilog HDL program. We also discussed the lexical conventions and the constructs. Parallelly, we have started with the data types. So, in continuation with the previous discussion, we are going to talk about the memories, parameters, and strings. These are comes under the category of data types. We know that a vector is simply a single element that is n bit wide. You can see here because bus is here a single element. This element is of 8-bit width, and here bool, it is also a variable, a single variable or a single element that is n bit wide. So here n bits is nothing but 32-bit data. We are having 32-bit. It is a single element. Okay. Then I can say that a vector is just a single element. But coming to an array, we studied the array also. So array are multiple elements that are L bit or n bits wide. I am having here multiple element, that means it is a one element, second element, third element. I am having here 8 elements for the count variable. This count variable is having 8 elements, and here also port id, this variable called port id is having 8 elements, and each and every element is of multiple bit width. So what is the width of each element here? It is a 5-bit width. And what is the width of each element in the count variable? It is a single bit width. So that is the difference between a vector and an array. Then what is this memories? So the hardware designers they have used the Verilog hardware description language to design the sequential or combinational circuits. Apart from it, they have a task to develop or to design the register files also. So the most commonly found register files in our digital electronics are the RAM chip as well as the ROM chip, which are acting as a primary or secondary memories. So these memories are also have to be modeled by using the Verilog HDL language. Okay, so in these memories, how to model these memories is, we know that each element of the array is also treated as a word and is addressed by a single array index. You can see in the earlier slide, that means here I am having 8 different elements. If I want to address this particular element, so what I am going to address this one, if I want to call this fourth element, means count of 4, because the starting address is always starts with 0. Count of 0 means this element will be extracted out, and count of 7 means this element will be extracted out. In this way we are using here single array index to address any element in an array. But coming to our memory, so here I also mentioned a point that each element of the array is an element, each element of the array, I have said it as an element. If that element is having a multiple bit width, I am going to use the word from now onwards. So WORD, word is having a multiple bit width. Now each word can be, I am saying it is can be a 1 or more bits, but we should have to understand the difference between a one n bit register as well as n 1 bit register. Why? Because here I am having, you can see in this membyte as well as in membit, this reg membit is there, reg mem 1 bit, actually reg membit 0 down to 1023. So it indicates the memory name is membit, and this membit with 1k 1 bit word. So membit is there. So how many elements I am having here? I am having 1024, that means 1k, and each element capacity is 1 bit only. That means I can say that this memory whose name is membit is having 1024 address locations or 1024 elements, and each element is 1 bit capacity. And coming to here, I am having one more memory organization, that is one membyte. The name of the memory is membyte, and this membyte is having 1024 different locations or 1024 different elements, and each and every element is having 8 bit width capacity. That means I am going to call this membyte memory unit as it is having a capacity of 1k 8 bit word, because I am saying that each and every element in your memory or in your array is a word. Element is also called as a word. So it is 1k 8 bit word or 1k 1 byte capacity. So this is about a memory organizations. Now the next one is parameters. Verilog also allows us the constants which are found in our program to be defined in a module. So module, of course, we know some of the constants, like for example, if you consider here parameter bus width equal to 8. So here bus width, it is a constant, and this constant is assigned a value called 8. Okay, so this is placed somewhere inside your program module, inside in your module. Now I am declaring the wires as well as registers in somewhere in the program, that is wire bus width -1 down to 0 bus. So what is the capacity of this bus? So we don't know what is the capacity unless and until it is being mentioned. If it is mentioned means I can tell that my bus width capacity is 8 bit width. Why? Because this bus width, which is acting as a constant, and it is also having a value, and this value is getting substituted here. So wire 7 down to 0 bus. This is the one what the compiler will understand. That means parameter bus width equal to 8 have to be exclusively defined inside your module, inside or outside of your module. So this is about module. So the next one in our data types is strings. So string is nothing but it is a combination of characters. How these characters can be stored in, can be used in our Verilog HDL is they can be stored in a reg by using a reg keyword or a reg data type. For storing the characters, we are going to use the reg as a keyword. So the width of the register variable should be very large to hold or to store the string. I am having here a string here, Ravan, R-A-A-V-A-N. It is of 6 characters. So these 6 characters have to be stored in the register variable. Here villain, it is a variable. It is of type reg. That means villain is a register variable. So what is the capacity of the villain of this register variable? It is 8 into 6 down to 1. So what is this 8 into 6 down to 1? Let me explain. Here I am having Ravan. It is having 6 characters. So for storing each character, Verilog requires 8 bit capacity. So the string the register variable should accommodate the string whatever you are sending, whatever you are sending to your register variable. So if each and every character is occupying 8 bit means definitely I require 6 into 8, that means 48 bits, because 6 is the characters I am having, each character is occupying 8 bits, that means 6 into 8 down to 1. That means how many 6 bytes I am requiring here. That means this register variable capacity is 6 bytes such that it can accommodate Ravan like this. Okay, and one more thing you should be cautious here is the width of this register variable, which may be here as a villain. It should be large enough to hold the incoming input string. If it is not large enough, that means some of the data some of the characters the register variable may not be storing inside it. So each register variable should be large enough to hold the string characters, and each character in the string, of course I said it is generally taking a 1 byte or 8 bits. For suppose if the width of the register is less than the string, what happens? So at this time what happens is the Verilog truncates the leftmost bits of the string. That's it. The leftmost bits of the string will be truncated. For example, a villain is there. Instead of 8 into 6, I have taken 8 into 4 down to 1. That means two characters the villain variable cannot store inside its register. Okay, so AVAN avan only will be stored in the villain register variable. That means RA will be truncated. Okay, in this manner. And for suppose if the width of the register is greater than the size of the string, simply what we are just appending the leftmost bits in your register variable with zeros. That's it. The most commonly used thing is just filling up the MSB bits with zeros. That's it. So these are the data types which frequently are used in our Verilog HDL programming. Now let us move to some of the system tasks and the compiler directives which are most frequently and notoriously used in developing any sequential or combinational circuit design by using the Verilog HDL. So what are the system tasks? System tasks. So these are nothing but it is the very frequently or routinely used operations. So what are the routinely used operations? Like in our C language, we are having printf and scanf for reading the data and for printing the output on the monitor screen. Those are the normal routine operations which will be found in the C language or C programming. Similarly, in our Verilog HDL also, for displaying information on the screen or for stopping execution or for finishing the execution also, we are having some keywords or usages or some system tasks here, system tasks keywords. So what are they? So all the system tasks will start with dollar symbol. So what is this dollar? Whenever you are seeing a dollar with a keyword, you should understand that it is a system task, because it is having some specialized privilege is there for the system task in our Verilog hardware description language. So like operations such as displaying on the screen or monitoring the activities of all your net variables, and if I want to stop the simulation or if I want to finish the simulation, we generally use the system task. So $display, this $display is the task for displaying the values of your variables or strings or input output ports or expressions on your monitor screen. $display is used. So like printf and scanf. Printf inside the brackets inside, you're going to call it as a sensitivity list. So whatever the data you would like to print on the screen, and you will be writing inside the braces. Similarly, in our Verilog HDL also, we familiarly use $display as well as the $monitor. So P1, P2, P3 is nothing but some data, which may be an expression, which may be a variables or strings or whatever it is. So this P1, P2, P3 are nothing but some data. This data will be printed on your screen. Okay. Now, so whenever you are writing any C programming, if you would like to print a decimal number on your monitor, like a equal to 5, b equal to 6, sum equal to a plus b. So sum equal to percentile d comma sum. This is the style what you will be following whenever you are writing the C programming. So that means here I definitely require some format specification. That means the variable what we are going to use in our dollar display, what is its format, like it is a hexadecimal one, the variable is, or it is a binary number, or it is a string, or it is some ASCII character, or whatever it is. So in order to make the compiler understand, we have to definitely give the format specification is must for every variable. So let us see some of the examples for dollar display. So dollar display hello verilog world, this whatever you are writing inside, it will be just printed as an output. And dollar display dollar time, so dollar time is there. Okay, so it is a dollar, that means it is a system task. Whenever dollar time is invoked, the current simulation time of the program will be generated as an output, that is 230 seconds or 230 time units. And reg 4 down to 0 port id dollar display, id of the port is percentile b, that means this port id, this is a variable, this variable I have to see this port id variable in binary format, that means I am specifying it by using this format specifier, that is percentile b. Okay, and next one is reg 3 down to 0 bus. So bus value is, what is the format specifier I have used here, again binary, that is percentile b. So bus value is 10xx. And the next one is dollar display, inside it I am having a, it is escaped identifier, multi-line, so it is not escaped identifier, it is actually a escaped character. So it is a backslash n means the next line. Okay, the I'm going to see the data in the next line. After a, multi-line string with a percentile sign. So first a will be printed as an output, after it new line, multi-line string with a percentile sign. This is how we are going to use the format specifier in the dollar display. Okay, then what is this dollar monitor? So here a speciality of dollar monitor is, it is having a mechanism to monitor a signal where the variable value continuously keeps on changing. So this facility will not be provided in your C language, it is only available in our Verilog HDL language. Of course the syntax will be same like dollar display, that is p1 p2, where p1 p2 will be up to signal names, variables or strings or whatever it is. So let us see this the usage of the dollar monitor by using the Xilinx tool now. The specialty of the dollar monitor when coming to dollar display is, dollar display I need to use many a number of times, but if I have used dollar monitor system task, the activity, for example I would like to do addition for a and b. Now a equal to 5, b equal to 2, next a equal to 6, b equal to 1, next a equal to 4, b equal to 7. So I am changing the signal values here. So for every time whenever I am changing the signal values and it have to be displayed in your console window, means definitely I have to use here 3 times dollar display. Instead of using 3 times dollar display, I just use dollar monitor a single time, such that it will continuously monitors whatever the signal values are getting changed, and it will be updated in your console window. So let me move with this one, Xilinx tool. So here I have written a program for 2x1 multiplexer whose inputs are I0 and I1. The selection line is S, and I would like to define inside the module the definition. I would like to go with behavioral abstraction. I said that behavioral abstraction is almost similar with C language or algorithmic procedure. So So I have defined here itself, inside here itself only. So input I naught I1, input S, output reg Y. Inside a sensitivity list only I have declared what are the input and output variables. And as the module definition is completely in behavioral abstraction, so the output for output variable have to be exclusively defined as reg by using a reg keyword. Now, always I am depending on my inputs. What are the inputs here? Yes, I1, I0. So, begin. If my selection line is 1, output is I1. Else, my selection line is 0. That means output is equal to I0. So, this is the concept of your 2 cross 1 multiplexer. This is how we have to design. It can be designed in our Verilog HDL. So then for this design unit, we need to develop the stimulus or test bench, because we have to check whether this design unit is functionally correct or not. That means we need to feed some inputs and check are the outputs are as expected or not. So this is how it is. So a module some TB, let me give the name as some TB test bench. So reg yes I1 I note. Why? Because these are the inputs. Now these inputs are to be declared with reg as a keyword, and this output have to be declared with y as a keyword. So what is the module name here? Mux behavioral. So its instance have to be present in the top, in the test bench. TB is my top module here. Inside my TB top module, I am instantiating mux behavior. This design unit I am instantiating. That means I am creating an instance, a copy, and that copy name is UUT. That means unit under test. This is the one I would like to give the name for my copy. And similarly, how like I0, I1, S, Y, in the same manner, I am going to use in the sensitivity list. So initial begin. So I0, I1, S. These three are the input variables. 3 input variables means I can able to get 8 different combinations, like from 000 to 111. As each time I am changing the inputs, means every time I am using here dollar display. Like I have changed here the inputs 000 for this one dollar display. Again I have changed the inputs. Again I am using here dollar display. So these many number of times I am using my dollar display. So what I will be doing here now is I just let me keep as some xyz or whatever it is. Okay, let me simulate this program, and all these 8 different combination of inputs, and what will be the corresponding output that is to be generated will be displayed in your console window, apart from your waveform schematic viewer, sorry, waveform viewer. Yeah, so this is the above is waveform viewer, and this is the console window. It is displaying me for 8 different 000 up to 111. What will be your y? That means I0, I1s, I0, I1s. So for different combination of your inputs, what will be the output that is generated? So this can be, that means here 8 different times I am using what dollar display. So instead of writing 8 number of times a dollar display, what I will be doing is the best idea. I use a single dollar monitor. Let me keep all this dollar display in your comments, single line comment I am using. So I am using here dollar monitor only. It is invoked only once, as dollar monitor is having a special mechanism to monitor the signal when its values changes. That means it is monitoring your output. This output is depending on your input signal values. These input signal values are continuously changing. That means it is definitely showing the impact on your output variable. That is why dollar monitor is a continuously monitoring mechanism will be there. So continuously monitoring means, let me run the program once. Simple it is. So I'm not using 8 number of times dollar display, I simply use it only one number of time. So all my inputs and the corresponding output will be seen in your console window. Some problem it is showing. What is that? Okay, has no port. Not required port, only not required. Let me check once. Okay, sorry, here I didn't give it a comment line. That is why I am getting the error. Now you are going to get your output. Okay, one more thing. I can even attach here also, no issue. I suspect again I need to modify the code somewhere. Okay, it's done, very good. So here I have used where in the program here I have used only once dollar monitor instead of 8 number of times dollar display. I just use it only one time. So in the console window, what happened, all 8 variables whose values are repeatedly changing, and the corresponding output will also changes. As the inputs are changing, the corresponding output will also be changing. So this is the use. This is why the dollar monitor have its own privilege in developing the Verilog design, any sequential design or a combinational design. So this is about a dollar monitor, and the very next one in our discussion is stopping and finishing. So what are this stopping and finishing is dollar stop and dollar finish. The task dollar stop is provided in our Verilog HDL to stop the action during a simulation. That means execution action is stopped for some time. Okay, the dollar stop task, it is making the simulation into be in an interactive mode such that the designer, for example the one who is developing the design, can debug the design from the interactive mode. That means because the dollar stop had put the simulation in an interactive mode, that is why the designer can debug the simulation now, can then debug the design, and he can check the activity what has been happened up to that line. Okay, that means here the dollar stop task is used whenever the hardware designer wants to suspend the simulation. That means I'm not completely terminating it, I'm just putting it in on hold state for some time. So he can examine the values of signals in the design. That means for the corresponding input, what will be the corresponding output, I can able to examine that. That is the usage of dollar stop. But the purpose of dollar finish is I am completely terminating the simulation. So that is the difference between the dollar stop and dollar finish. Let us again move back to our Xilinx tool. Okay, here I have written some example code. Clock equal to 0, reset equal to 1. After 5 seconds, reset is equal to 0. Okay, good. That means as $50 stop. That means here I am suspending the simulation at 55 seconds. At 55 seconds it should be not 50. And as a $60 finish. That means 55 plus 60, 115. I am completely stopping the simulation. This is what the difference between dollar stop and dollar finish usage. Okay, let me move back to Xilinx tool again. Okay, so here what I will be doing is I just remove the comment lines for dollar stop and dollar finish. So actually I have to generate all 8 different input combinations, but as soon as dollar stop is encountered during the time of execution, I cannot able to find in the console window the 8 combination, that is 111. Let me check with the program. Let me simulate it now. Only 7 different combination of inputs only I can able to find in the console window. Yes. So only 7 0 0 0 0 0 1 1 0 0 1 0 1 0 1 0 0 1 1 1 1 0. That means I didn't find it anywhere stop combination. That means 1 1 1 combination I didn't find. That means I have made my simulation to be in an interactive mode. That is what it is happened here. Dollar stop had put the simulation in an interactive mode. So up to here I am checking whether all the inputs and the corresponding output are correct or not. Like I0 I1 yes, I0 I1 yes, I0 I1 yes. I just cross check whether for the corresponding inputs the corresponding output or the expected output is generated or not. Okay, if it is generated means I don't have any issue and I can resume. That means I can resume the simulation from the suspended mode or an interactive mode like this. Again I can resume. Yes, I have resumed my simulation and the next input combination is 111 and the corresponding output that I have got generated here as an output as 1. So this is the usage of dollar stop and dollar finish. Okay, so at what seconds dollar stop is occurred? At 1 second, not at 1 second. Yeah, it is 1 2 3 4 5 6 7 8. At 80 second afterwards dollar stop is generated and at 90 second dollar finish is generated. Let me check in the waveform window also. This is 4 seconds, 5 seconds, yeah, 8 second. That means up to after 80 second what happened? 111 activity started. Up before 8 seconds all the 7 combinations like if you can see here 0 1 1 like 101, all the different 001 different combinations you have seen here. And after the 80 second 111 combination you are going to see, for which the corresponding output will be 1. In this way the dollar stop and dollar finish are extremely and highly useful in designing the Verilog HDL program. So let me move with the next discussion, that is compiler directives. So what is this compiler directive is? These compiler directives are the directives which are also found in our C language. The most commonly used directives, we call it as a preprocessor directives in our C language. Those are hash include, like hash define. In the similar manner, in our Verilog HDL also, we do have tick define and tick include. So what is this tick define and include are? Tick define directive is used actually to define a text macro in our Verilog HDL. So the Verilog compiler normally what it will do whenever we are telling it to compile a program. For suppose, let me take one new project, file, open project, replicate full ladder. Yeah, let me open this project. So what tick define will be doing is, it is used to define a text macro in Verilog because this entire script is in Verilog HDL language. So tick define m dollar monitor. This dollar monitor is nothing but m is a text macro. I mean, it is a text. Whenever this text is encountered in our program, it is immediately being replaced with what is its definition, what the text macro, what is the definition of this text macro, that is dollar monitor, like tick m is there. So tick m is encountered in some of the line in your Verilog HDL program. So this tick m is being replaced with dollar monitor. Okay, that means I can say that Verilog compiler, it is substituting the text of the macro whenever it is encountering a macro name. The macro name is what here? M is a macro name, and what it is doing, it is substituting the text of the macro. What is the text of this macro? This is the, if it is a macro, means the text of the macro is dollar monitor. So whenever I am compiling Verilog, whenever I am doing the compiling like this, okay, so as I have done compiling now, check syntax, it is correct. That means it is properly compiled. So during this time of compiling, the Verilog compiler, what it do is, it is substituting the text of the macro as it is encountered here, tick m. If suppose I didn't declared any m here, and I am again compiling. Will it compile or not? We'll see. No, it is not compiling. Why? Because that for this text, for this macro, I didn't have any text. That is why. If I give the text for this macro, yes, it will be definitely compiled. Like hash define pi 3.14. How you have used it in the C language, in the similar manner, we are going to use tick define directive. So initial dollar tick m, that means dollar monitor. So it is some full adder. This is what we are going to get, and let me check, will be getting the output or not. C in A and B. This is actually a 4-bit full adder. I mean 4-bit triple carry adder actually. Where I have done mistake. Okay, I will rectify that anyhow. C in equal percentile T. Equal to 4-bit binary 1 0 0 1 1, that is 3, and this is 4-bit binary 0 1 0 1, that is 5. It is enough, I think. Otherwise, let me substitute these values again. Copy, paste. 0 1 1, that is 7. Enough. Only one value I am changing. Let me recompile. It won't compile because I have committed some mistake here. That's why I am closing the window. I came to know what is the mistake I have done. Now we are going to get the output. So 3 plus 5, and next is 3 plus 7. 3 plus 5 is 8. 3 plus 7 is 10. 8 and 10 should be my sum S out. That is S out is 8 and 10. Okay, so here Cn is 0, A is 3, B equal to 5, A equal to 3, B equal to 7, S out is 8, S out is 10 here. Okay, in this way we can able to get the output. As what the compiler had substituted the text of the macro. So this is the macro and its text is being substituted here as soon as it is encountered with the macro name. This is the usage of tick define. And let me move with the next compiler directive, that is tick include, like how you have used hash include stdio.h or hash include conio.h. In a similar manner, the same usage can also be found in our Verilog HDL. So tick include is similar with your hash include in your C language. So generally what happens, the preprocessor directive hash include, for example mat.h, all the mathematical function definitions are provided in your mat.h header file. And similarly hash include stdio.h, all the standard input output function definitions are present in your stdio.h header file. That means whenever you are using printf and scanf inside in your C language programming, so the compiler doesn't know until and unless you are providing your hash include stdio.h. If it is not given in the program, that means preprocessor directive is not there in that means you didn't provide it, so the compiler will not be compiling the program. So this is the usage of tick include or hash include in your C language. Similarly, tick include is playing also a vital role in our Verilog HDL. So I have used tick include half adder.v. For suppose I am going to design module full adder, some a comma b comma c s comma c out will be its sensitivity list ports. So the full adder is constructed by instantiating two half adders like HA, one copy is H1 and HA second copy is H2. So this HA definition should be present in your Verilog HDL program, but like instead of providing the definition below your full adder module definition, you can also separately write the definition for your half adder in the same folder and key, and it can save save the text file as .v, like ha half adder.v. This is the name you given. Okay, let me explain with you with this like Xilinx experiment. So I am having here a like 4-bit triple carry adder. FBRCA is the module name which you can able to see here, and 4-bit triple carry means I generally require 4 full adders. FAB as the full adder. So how many number of full adders I have used here? 4 instances or 4 copies. Okay, so after this one I didn't so I can provide the definition below. FAB definition I can provide below like this, but instead of providing the definition of FAB in this below of your FBRCA, what I would like to do is I want to use FBRCA is there. FAB 4 number of times I have instantiated, and I am just compiling this one. Will it be getting compiled or not? Let me check. Okay, it is getting compiled because some or the other way it is attached. Okay, so but here I can able to find the question mark. Question mark means therefore check syntax is, it is just checking the syntax. It is just only the purpose of check syntax is whether you have placed the semicolon or a comma and all the keywords properly or not, only it is seeing. But here FBRCA under it I can able to find the question mark, which means that the definition hasn't been provided. So if the definition hasn't been provided means during the time of simulation here, because it is the simulation module or the simulation block, you can see you will never be getting the output. See, as I have told you, right? Because the definition is missing actually. Okay, so you can see line 28 FAB is there. FAB definition I didn't provide it. So in order to overcome these things, I need to provide a definition of your FA. So how I have provided definition of your full adder is in the same folder I have designed the full adder definition and named it as fab.v. So in the same word, in tick include fab.v. Now just saving it. I am including this file. Which file? fab.v. Like for example, you are going to do the C programming. So what is the extension you use it to keep is .c. In the similar manner, I have designed a full adder and given the and I have designed a full adder in Verilog HTML, and the file name I have kept as FAB for my full adder with an extension as .v, which indicates it is written in Verilog HTML. So that file I have included here in my programming. Which programming? FBRCA. So tick include FAB.v have already included in my programming. Now what just we'll see fab.v definition here. Yes, so fab is a full adder, single bit full adder. It is abc sum comma carry. Inputs are abc, output is sum and carry. S sign sum equal to ax or bx or c, right? Carry is ab plus bc plus c, right? The definition is clear. Now again check with this one. So now everything is present, and FAB definition will be extracted from this preprocessor directive or called as compiler directive. This compiler directive is providing the definition for this FAB, and everything is present in my programming, and it is ready for the simulation, and I can able to apply the stimulus confidently and check the outputs. So let me check the output now. The same 8 and 10 should be generated as an output. That's it. So here you can see a equal to 3, b equal to 5, s of t is 8, and a equal to 3, b equal to 7, s of t equal to 10. In this way you can able to get the output. So this is about the system tasks, that is a $display, $monitor, and the compiler directives. Those are tick define and tick include. So these are the concepts which are playing a crucial role whenever you are going to design any sequential or combinational logic in Verilog HDL. So that's it for today's class, and have a nice day.